Okay, here we go. What is a net accumulation function? When we say net accumulation, what do we mean by that? Those values. And that was his question. Yes, sir? The amount that's been accumulated since the starting time. So the amount that's been accumulated since some chosen starting time. Or it's the amount of change since that starting time. Right? It gives the amount of change in a quantity for any value of x when the rate of change is known. And I should have said given some specific starting time. Maybe it's 1 second or at 5 seconds. And then that function will tell you how much change since your designated starting time. All right, and then we talked about changing rate of change. Changing rate of change is very common, right? So there are some things in the world that have constant rate of change or almost constant rate of change, but there's many things in the world that the rate of change is changing. So we talked about this example here. And then principle 4 was we're going to make a pretend rate function because with continually changing rate of change, we can make no progress towards accumulation. What do we need? We need constant rate of change to get changes in our variable, our dependent variable. So with constant rate of change, we mimicked. So like, for instance, if I had some rate of change function like this, we said, okay, let's try to reproduce it with constant rates like this. And then, if we got a constant rate, say that's m2, then we know how much change came from that constant rate over this interval, delta x. How much change do we get at rate of change m2 for a change in x of delta x? How much change do we get? Oh, please know this. I've got my constant rate of change. I've got a little change in x. So how much change in y will I get? m2 times delta x, right? Will be my dy for that second interval. So here I can make now, with these constant rates, I can make progress towards change in y or building a change in y function, right? By using mdx. And then we sum all of them together, right? If we're accumulating over several intervals, we sum the first mdx plus the second mdx plus the third mdx. And by adding those up and accumulating, we're building an approximate net accumulation function. Okay, so then we said that there was the sum of all those changes in y from the completed intervals and a little bit more change from the current interval that's not completed yet. Cool. All right. And then the next one was make more smaller intervals, right? More smaller intervals means a better rate function and a better net accumulation function. And then taking that to the extreme. So here's for that flag lowering problem. Here's a pretend function with really small intervals. And you can see it's doing a really good job replicating the original rate function. So from there, what do we do? Super small intervals, right? Super small intervals means we can't tell the difference anymore between approximate rate and approximate accumulation and exact rate and exact accumulation. So with super small intervals, now we're like converging on our goal, right? Which is the exact net accumulation. So our approximate net accumulation is this. And so we let delta x get really small, super small. And so what we called AX, our approximate accumulation, becomes exact accumulation, net, right? These are net. And then what does that become? That thing is essentially, or shorthand for that, for the summing up of all those changes, is integral, right? Integral from a to x of the rate times dt. And we're going to talk more about that in a second. And what happens to that as delta x gets really small? So if delta x is really small, well, dx is like a partial interval. It kind of disappears. It's negligible, right? It doesn't matter anymore because they're all small, right? They're all teeny tiny intervals. So this doesn't really matter. So for delta x small, that approximate accumulation function, we write it shorthand, or this new notation is the integral. Okay, so let's, and that's our exact net accumulation. So before we do principle 7, which is total accumulation, let's investigate this more closely. Like, let's look at how is this integral notation the same as our approximate net accumulation. So here we go. Exact accumulation function. So there it is. So we want to think of this as this. Okay, so we think it came from this. So we think of the integral function as the summation of rate times delta x plus r dx. But what? When with a value of delta x small enough so that the values of approximate accumulation are indistinguishable from exact accumulation. And so then when that's true, then what happens to the accumulation due to the partial interval? It has virtually no contribution to the accumulation. So watch, ready? Okay? So but that's only when delta x is small enough, right? So if delta x is big, then that partial interval is important. It makes a difference. But when delta x is small, it just doesn't make a difference anymore. So we think of the integral notation as this summing up m dx plus m dx plus m dx plus m dx when the delta x is really small. Okay, so now I got 4 questions for you. How are they the same, right? So how the notations have parallels, right? It's parallel notations. So we want to see how they're the same. So in each of these two, you're going to identify where in both of them do you see, number 1, you know how fast something is changing. Where do you see that in both of these? And then number 2, you want to know how much of it you have. Where do you see that in both? Which is found by summing up. Where do you see that in both? And then finally, many bits of change, like delta y's, or when delta x is small, dy's. So and to forget about 7, we don't want to do 7 and 8. So get a partner, group of 3, you're talking through 1 through 4. So for each of those, 1 through 4, where do you see it in both of these expressions? All right, go. So we know how fast something is changing. Where do you see that in the first one? So in this one, in our integral function, where do we see we know how fast something is changing? What is that? The rate of change function, right? And what about here? The approximate rate function, right? This is like our pretend step function, and this is like the actual changing rate function. That's this premise of we know how fast something is changing. So there's those. Okay? We want to know how much of it we have. Where do we see that in the first expression? We want to know how much of it we have. Where's that? It's the whole function, right? It's the dependent variable of this function, right? And what about here? A of x, right? So we know how much of it we have. So that's the net accumulation, right? Whether it's exact or approximate, which is found by summing up. Where do we see in the first one summing up? Integral, and in the second one? Greek. So this is German S. The top one is German S, stands for sum. The bottom one is Greek sigma, stands for sum, right? Summing up changes, right? Summing up changes, accumulating changes, right? That's why it's a net accumulation function. All right, and so where do we see a bit of change in the first one? What represents a bit of change that we're summing up? What represents a bit of change in the first one? Yeah. Nope. A bit of change. Yeah.
dt?
Nope, not dt. How do we get bits of change? It was the most important thing. That's like the most important principle this is all based on. Where's a bit of change? Someone in the back. Yes? Nope. Yeah. Yes, guys, yes. dy equals what? M dx. What is M dx? Little bit of change. And then we're going to accumulate those, right? So number 4 is that. That is a bit of change of our dependent variable. That's what we're summing up. What are we summing up? We're summing up M dx's, right? We took the constant rate on the step, we multiplied by the delta x, and we got the amount of change for that interval. Then we did it for the next one. We took the step, got that constant rate, multiplied it by the delta x, got the change for that interval. And what do we do to get the function? We accumulate, we add them up. That's what the sigma and the integral is. Okay, so when you look at an integral and you say, oh, summing up changes in my dependent variable, how are those changes calculated? By rate times change in x. By rate times change in x. Does it make sense? Come on. There we go. All right, so let's practice here. So when you see this, when you see this, you should think that this is what? A net accumulation function, right? So even though that might not be written, you might just be given that integral expression. You see that, but you think, oh, that's a net accumulation function. So tell me something about that net accumulation function. Tell me anything. It's a net accumulation of what? Yeah. Starts at 3. So it starts at, when our independent variable is 3, we're going to start accumulating from there. What else? What's that? Right, so the x, our dependent or independent variable, is kind of where we've accumulated to, right? And that's increasing, right? That's increasing. What else about this net accumulation function? He said the rate of change is square root of t. Agree with that? Yep, the rate of change is square root of t. So here's one way to write it. And so I don't want you to just copy it this way, but in your own words, here's one way to explain this. This is the exact, I should say exact accumulation of changes in some quantity f, right? So what are the changes in? The changes are in quantity f, right? Due to its changing rate of square root of x at every moment from 3 to x, right? At every moment starting from 3 to x with a rate of change of delta x, that expression will give the net accumulation. Okay, so I want you to practice, and I try to write it in your own words. Don't just take this exact template of a sentence and change it. But for these two, so first of all, when you look at it, you're going to think, okay, this is some accumulation function, a net accumulation function, and then you're going to describe what net accumulation function it is. And what about this one? 0 to 12, w squared minus 7 dw. Is that a net accumulation function? Is that thing a function? What is it? Expression. Okay, does it relate to a function? All right, and so what is it? So if there is some function involved here, what is it about that function that this expression is from 0 to 12? What's that? Okay, you get a number for this. You get an amount of accumulation, but we still want to think of it relating to a function. And so if we said it related to a sub f of x, then what would this be related to some function a sub f of x? Function notation would be a sub f of 12. It'd be one value of the function, right? It'd be a particular value of the function that would be represented as. Oh, jeez. I could represent this as a sub f of. Right, so you imagine that there's some function a sub f of x. Well, this is one particular value of that function. It's what you get if you evaluated it at 12. So it's a number, it's a value, it's one particular value of some net accumulation function a sub f of x. The one that you would get when x equals 12. Okay, so I want you to just practice with the person, explaining to the person next to you what this expression means and what this expression means. Just take a minute. And again, don't read the sentence I wrote with different things substituted, right? So see if you can say it in your own words, what that means and what that means. Go, take a minute or two. Okay, so here's one possibility, something totally different, like structured totally different than the first one. I said this is the exact net change in a function, say f, as u changes from negative 4.8 to x, if the rate of change of f is the sine function. So see how that's totally different. It's the same meaning, but I wrote it in a totally different way. So it's the exact net of change in a function f as u changes from negative 4.8 to x, if the rate of change of f is a sine function. Okay, and then we said that was a of f of 12. Here's another way to say it. I said this is the exact net change in some quantity having a rate of change of x squared minus 7 as x changes from 0 to 12. So you should be, understand it well enough that you don't have to just take one of these sentences and substitute new stuff in. Okay, you should conceive it well enough that you could come up with something like this or slightly different. Okay, any questions on meaning of these integrals? Yes, please.
On the third one,
yeah.
The independent variable had to be the top number. Could it have been 0? Could that have been a of f of 0?
Usually not. Maybe there's some way, but that would be way out of convention. Yeah, normally we do the starting value at the bottom, and then the value of the independent variable at the top. Yes, please.
Do you not mention, like, in the first two, so like in a function, say f or quantity f of x, do you not mention that in the third one because it's a of 12, not a of x?
Yeah, so we want to think of it as a function and then evaluating that function at 12, but it still has meaning without. It still has that same meaning without like specifically saying the function, because it's the net accumulation from 0 to 12 of some quantity. So I mentioned it. So actually, I mentioned it here without naming it. So I said some quantity, right? So that is f. I just didn't name it, right? Other questions? Okay, so here's a practice example for you. Maybe. Comes. All right. So when Katie unties a partially filled balloon and inflates it with more air, the volume increases at a rate of 2 over x plus 1 inches cubed per second, where x is the time elapsed since Katie began inflating the balloon. If the volume of helium in the balloon is 18 inches cubed at x equals 3 seconds, write a function for v of x, the volume of air in the balloon at x seconds. See if you can do that. See if you can do that based on what we're talking about. So can you write, what does v of x equal? So what does v of x equal? Okay, you're either making progress or you're getting help, or you're helping someone. If you help someone, you're not just telling them what you did. All right, so if you're helping someone, maybe give them a hint and don't just tell them your answer. Okay? Well, let's see if we can do that.
What we're curious about is the 18
Okay.
aspect of it, and we needed to add that on first.
Okay. So what?
Otherwise, we did the integral of x,
The integral of
and then x, well,
3
3 to x,
to x.
and then the 2 over x plus 1
Okay.
times dx. Oh, not dt, excuse me.
Okay. Do you want to switch these to t's?
Yeah.
Yeah. So
Yeah, that's it, the x is
so that's the question. Why can't we just put x's there and an x there? It's like a 5-minute conversation. Okay. And we kind of want to move on, but it's important to use a different. Well, no, it's because we're going to integrate from 3 to x. Well, x stands for this point, and when we go from 3 to x, what we're going to take we want to be accumulating everything from 3 to x, right? So we need a different symbol that represents all the x values from 3 to x, where x is kind of at the right end of it. That's why we need a different symbol. So we can use u or t or whatever you want. And so it's representing, as we accumulate from 3 to x, every x value in there. But x itself is just at the very right-hand side. So, right, we're going to come in here. That. And so you want to do t. T is our generic choice, but u, v, doesn't matter. Anything else? Anything different than this? Okay, how'd she do? So the question, but they weren't sure about adding 18 or not. Do we need to? So what is just the integral? So what does just the integral represent? Right, so like in terms of the problem, so like in the context of the balloon and the volume, what does it mean in terms of the balloon and volume? That what I put a box around. So you'd say it's how much what? How much the volume changed? Since 3 seconds, right? Starting at 3 seconds. And we want to know how much it's changed since she began inflating the balloon, which would be at x equals 0, right? So if we want to get that, if we want to get how much she's inflated in total, then we're going to take all the change in air, or volume of air, starting at 3, and then do we need to add the 18? Yeah, we need to add, if we want the total accumulation of air entering the balloon, we need to add everything from before we start the bit-by-bit accumulation, which is the integral. All right, so is there another way to write that then? Vx equals? So we get the integral 3 to x, 2 over t plus 1 dt. So I could write 18 plus, or what else could I write here? V of 3. That's what 18 is. It's V of 3. So it's everything up, all the air that's entered in, all the volume accumulated up till 3 seconds, plus the additional accumulation, or the change since 3. Because that's what 18 is. 18 is V of 3. Okay, questions on that? Does that make sense? So now we've answered the question of the difference between net accumulation and total accumulation. Okay, cool. Net accumulation would be just the integral part, starting from the 3. If we want total accumulation, then we have to include everything that's accumulated before, right? That's like as a lump sum, right? Questions on the balloon problem? Okay, we've finished it up. So then the exact total accumulation, we know exact net accumulation is our integral expression, exact total accumulation. Then we're going to add all the previously accumulated amount to get the total accumulation, which is now how much you have at every moment, right? How much you have at every moment. And that means add f of a, right? So if it's the f function is our total accumulation, we have everything from before, f of a, then plus the bit-by-bit accumulation that we're tracking starting from A. So we made it so this is the full journey here, principles 1 through 7. Okay, let's take a look at that total accumulation function or amount function. And if we subtract f of a from both sides, we look at the right. We know we have what's that? That's exact net accumulation. So then the left side must be exact net accumulation also, but just expressed in a different way, right? So both sides express exact net accumulation or exact amount of change, but in different ways. On the right, it's like final minus initial. So it's like the final accumulation minus the initial accumulation will give you the net change. So this is the idea that subtraction, a difference, can give you amount of change, right? Subtraction has that meaning of amount of change. And then the right side, of course, we know means the net change by accumulating many small bits, right? And what's one bit of change? What's one bit of change in that expression?
Oh, it's R of F.
This whole thing, right? We're summing up bits. This whole thing is a bit, right? This is multiplication. M dx, right? M dx gives a little change in y. Right? So the dt is just not like this like afterthought. You don't just tack it on there because you're doing an integral. It's part of the math. You're multiplying by a change in an independent. M dx, right? It's part of the math. It's not just telling you what our variable is. M dx, that's what this is. Multiplication. We're multiplying two things together. Okay. And then maybe that looks familiar from Calc 1 now. So when we subtract that f of a from both sides, everyone recognize that? Yes, please. Yeah, this is the fundamental theorem. So when you take your total accumulation function and subtract the starting amount from both sides, you really have the equation that represents the fundamental theorem of calculus. Okay? So it expresses the net accumulation function or amount of change in two ways. Left side, accumulation of bits of change, right? Accumulation of bits of change. Right side, final amount minus initial amount. Two different ways to express net accumulation. And then this fundamental theorem was also kind of the key to solving these, right? So if we wanted to know what that amount was, instead we figured it out by solving it this way, right? We'll get to that later. From here, at this point, we're just going to practice setting up our net accumulation functions as integrals and interpreting those, and letting GC do the work in terms of solving, right? So GC is powerful. It can solve these really fast. So we're just going to focus on the meaning of the integrals for now, for a couple weeks, and let GC do the crunching. Okay. All right. So we got exact total accumulation gives the total amount. Exact net accumulation gives how much f has changed since A. We've got that down. So if we need to write a function f, a total accumulation function, or its net accumulation function, then what do we need? And this is going to be the theme for the next month or the whole course, we could even say. Okay, so we need to find some total accumulation function or net accumulation function. That's going to start by figuring out what. If we have what, then so this is telling us that all we need is really one thing, and we can write down the total accumulation function. What is it that we need?
Yeah, the bit of change or the MDX, right?
The rate of change function, right? We need the rate of change function. If we have the rate of change function, we just write this down, and we wrote out what the net accumulation function was. Or likewise, we need the rate of change function and a starting amount, and we have the exact total accumulation function. We just write it down. So if we want to, suppose we need the rate of change function for f. That's what we need. If we've got that, we can write down either net accumulation or total accumulation function. Okay, so we're going to start here today by talking about an area accumulation function. We're going to focus on the quantity of area. So if I want to write an area accumulation function, what will I need to do that? He said the rate of change of the area. Agree with that? Exactly, right, exactly. We need the rate of change of area. If we have the rate function for area, then we can just write it down because we know what net accumulation is if you know the rate. That was the endeavor, right? You know how fast something is changing at every moment. You want to know how much you have at every moment. So that requires, if we want to know how much of what we have, it requires knowing the rate. And once we know the rate, we can just write down the function. So using integrals for area. So we need to determine the rate of change of area. And one other issue, which we'll talk about next time, we need to investigate the impact on the integral of values of intervals where the function values are negative. Okay? So let me just explain that here. Let's look at this here. So we're interested in so I've got, say, this function f. Here's what I want. I want a function that tells me, starting from 1, okay, starting from x equals 1, I want a function that tells me the accumulation of area starting from 1. What area am I talking about? I'm talking about the area between the function and the x-axis. Between the function and the x-axis. So that's the area, this green shaded region. So you see that it's a function because as x increases, my area changes, right? My area changes, so it's an area function. So what do I need then to write this area accumulation function? I need rate of change of area, right? If I have rate of change of area, then I can just write this down. And what will it be? So say I want the net accumulation of area. So, and I have, say I have the rate of change of area. I don't yet. I don't have it yet, but suppose I do. How would I write down what the net accumulation of area is? Okay, it'd be the integral from 1 to 3, or from 1 to 3? Not 1 to 3. I want the net accumulation function. I want it for all those green shaded areas. Yeah. 1 to 3 will just give me what? One value. I want the function. I want every single one of these for every x. So I'm going to go from 1 to x of my rate, area, t, oops, oh my goodness, wow, something went wrong there. Let's try this. Control 9, there we go, t, there we go. Is that it? That would be it. If I have that rate of change of area function, then I would just do my integral from 1 to x, the rate of change of area, t dt, and that would be my net accumulation of area. And then we'll just let, if we need to find particular values, we'll just let, for instance, if I say if I wanted it at 2, so it doesn't like something I've typed here, probably because of these subscripts. Oh, probably because this is defined in GC. But if I define this function in GC and define my net accumulation, all I have to write in is a sub area of 2, and it's going to tell me what the answer is. It's going to tell me what that value of that function is, or the net accumulation of area up to 2 from 1. But it's not doing that. It's not giving me the equals answer because we haven't defined this in the program. Okay, we haven't defined what that rate of change is. Okay, so how are we going to do this? How are we going to figure out? So now we got to figure out what is the rate of change of area. So what is the rate of change of area? So like we did before, we're going to start with the most basic case. What's the most basic case of the function? It's going to be the easiest. Constant function, right? Just like we talked about, we're able to do it with constant rate of change, right? So let's start there. Let's start with constant rate of change, and then let's talk about how we could do it with a changing rate. Okay, so I've got my independent variable here is x. And then my dependent variable is, now this capital A, can I just say capital A now to mean area and not approximate net accumulation? Are we okay? So now that in this context, capital A means this area function. And so say x is in the units of inches. And area is in the units of inches squared. No, sorry. This is also inches. This is the height of it. So the area is the area of the blue, right? So this is inches on this axis and inches on this axis. And so then that function a of x would be in inches squared. So the question is, what is the rate of change of area with respect to x? So let's just look at it here. So what is the area? So at x equals 6, what's the area? Area is 18. All right, so we'll call that like x initial. And then if I go to x final, say 7.5. So x initial is 6. X final is 7.5. What's area final? 7.5 times 3, 22.5, is that right? Okay, so how much did x change? How much did the area change? Okay, just give me 1 minute, okay? So we got a change in x of 1.5, change in area of 4.5. That means don't pack up. So when I say give me a minute, it means don't pack up, because you pack up and the person next to you, and then everyone's packing up and no one's listening. Okay, so delta x 1.5, delta a is 4.5, and so what do we say? dA equals mdx, right? So we got our change in independent and our change in area. And so here's one particular example. When the change in independent is 1.5, the change in area is 4.5. See that? Which means that rate of change is 3. Okay? And that's what? That's the height of the rectangle, is 3. And so if this were a function, so if this is the function f, what is the definition of f? F of x is the constant function 3. Notice, my rate of change of area is the same as the value of the function. This is the huge theme of area. The rate of change of area is the same as the value of the function, not the rate of change of the function. The value of the function. The value of the function. Okay, your homework for Wednesday is posted.